its regression line and what it tells us. So there are different calculations that we've talked about, like deciding if something is linear or not, right? We said we can look at the scatter plot and see, does it look like this follows a linear pattern? Does it look like a line would describe it? How did we get more precise than just looking at it? We did the R value, the correlation coefficient, which our calculator can tell us. I need everybody make sure, not all my calculators I think have been picked up and the diagnostics turned on, so make sure the diagnostics are on your calculator. We'll need that today. So that was when you went into math, or sorry, catalog, second 0, and then scroll all the way down to diagnostic on. Because I know people keep picking up calculators that hasn't been turned on, and so they're not getting the information. And then it should say diagnostic on and just hit enter. So that way we're all ready to go. And how do we decide from that R value if it was linear or not? Yeah, we had to look at that chart. We know 1 or -1, those are both perfect linear relationships, just either if it's increasing or decreasing. Something close to 0 is not linear, but that table showed us how close it had to be for it to count. Because basically the more points you have, the smaller your R had to be. There'll be a little more variation. There are some other calculations that you could be asked to find. Coefficient of determination is not something that I'm going to use frequently, but you could hear about it. It's R squared. It's basically your correlation coefficient squared. That way it takes out whether you're looking at a positive or negative relationship and gives you an answer between 0 and 1. 0 is still a poor relationship. 1 is a strong relationship. The best use of this is talking about the meaning, like in terms of a percent, what percent of our variation is explained. So if it's a perfect 1, it means 100% of the variation is explained by the line. You know, your Y values change, right? And it's saying every point's on the line, so 100% of the reason the Y's changed was because they followed the pattern of the line. Whereas if you have points that aren't on there, it would be a smaller percentage. So, deviation. We've talked about standard deviation. Deviation in general is just talking about how things differ from the mean. How different are they from our average? And there's really 2 types, explained and unexplained. So explained deviation is anything where the variation is explained by the regression line. If you're talking about a line, it's not surprising that different x values have different y values. We kind of expect that. That's explained variation. The y's are different just because they're at a different place on our line. Unexplained deviation is anything else. So something else that made these values vary. So what I want to do, I'm going to put an example that we've looked at several different times, our drilling data that we've seen, and I want to find the coefficient of determination for this data. So coefficient of determination, that's our R squared. We have to start by entering everything into our set. Did everyone get their data entered? And so we're going to do our regression line again. So we go to Stat, Calculate, number 4, our linear regression, which should just say X list is L1, Y list is L2. And since we all turned our diagnostic on, we should all get something that looks like this. And what we're used to looking at on this screen is either the Y or the R value. It actually does give us the R squared, the coefficient of determination. It is if you just took the 0.7728 and squared it. So you could get it by hand if you know R, it's just squared. But our calculator tells us that. So our coefficient of determination is R squared. So 0.5973. What this is a percentage. It is telling us that 59.73% of the variation in our Y, which was our drill time, is explained by the regression. So we would expect every depth to have a different drill time, right? The deeper you need to drill, then the longer it will take you to get there. We expect that. So we expect these Y values to be different. There should be variation. What this is saying is our line accounts for 59.73, almost 60% of that. Now, not all the points are on our line, so that's where that other 40% of unexplained variation comes in. For whatever reason, it wasn't just a perfect line, so there were other factors that impacted.
So 60% is based solely the depth differences, and the other 40%, 40.3 is
right, and things we don't have the power to know from this situation. Okay, any questions there? The next slide, I just put a diagram, kind of give you a visual. Data set A, is every point perfectly on our line? I mean, our line goes through them. Some of them are, just barely above or just barely below. That's a situation where it's like 99.99% of the variation in our Y is because of the line. We expect our Y's to be going up. They do almost perfectly. This one is a little weaker, 94.7%. We can see it's still basically a line, but there is a little more variability. Not every point is on line. Here, we have a lot of points off our line. Okay, it doesn't explain the data very well at all, so that's like a 9.4%. So basically what you need to think about in your head, the more closely it matches the line, the closer to 100% it will get. Okay, a very poor model would be very close to 0. All right. The next topic that comes up is residuals. So we've talked about residuals, right? We touched on that yesterday. Look at your formula sheet if you have to. What is a residual? Observed minus predicted. Okay, it's the difference in what happened in our data and what we expected to happen because of our line. Because we know the line's not perfect. We can use that information as another way of deciding if the linear model is good, to check out if there is a constant variance, if it's equal all the way along, and also to look for outliers. How else did we look for outliers? The box plot. Remember we did like upper and lower fence to calculate it. We can also get outliers from here. To do that, we will look at what's called a residual plot. So a residual plot is basically plotting those differences. Actually, let me go back. I'm going to write a couple things on here. When we start talking about these residual plots, we're looking for a couple different things. if there is no pattern when we look at these graphs, it means it is linear. The reason we have to look at that, the correlation coefficient, remember that tells us how close to being linear it is. There are situations where it can imply there's a linear relationship. When it's really not. So maybe, remember, that tells us how linear something is, but it doesn't tell us if a different model might be a closer match. So maybe a linear model is like 75%, but a quadratic model would have been really, really good there. The correlation coefficient doesn't tell us that. Residuals do. So residuals check for that situation where the correlation coefficient tells us it might be linear, but there's something else that might be a better match.
Is the correlation coefficient the one where if it's a parabola, then it says it's really poor correlation? You know
Yeah.
what it is actually?
Right. There's a pattern, but it's just telling you it's not linear. It doesn't tell you that there's a different type. So for example, I put a couple residual plots on here. So residuals, we know, are the difference between our observed and our expected. If we plot that, and I'll show you how in a minute, we get a plot that looks like this. What we are looking for is no pattern. Because this is the difference between the observed and the predicted. If there's a big pattern there, that means something else was a better fit. This one doesn't have a pattern, so it is linear. This one is not, because what it's telling us is at the beginning, we had over approximation. In the middle, our line was an under approximation, and then it became an over approximation again. So there's a pattern there. When you look at those residuals, if it forms a shape, that's bad, because it's saying our line was predictably wrong, in essence. Here it was always over, here it was under, here it was over, so that's bad. We can also look at things like over time. This is what's called constant error variance. It was a good model at the beginning, but what's happening as time goes on? It's getting worse, and we can see that in this data. At the beginning, it's a pretty good model, but then at the end, these points are getting further and further away from our line. So the linear model is becoming less accurate as we go on there. So this would be another situation where it's not linear. Outliers. Okay, if we are looking at a scatter diagram, we can see this one kind of looks like an outlier, but it may not throw up a red flag. It's not hugely different from the others. But if you look at a residual plot, it is, because we can see all these points are right down here, except for we have one way out here. So those are situations that the residual plot can show us. So we're looking at, does it have a pattern? Does it get wider as it goes on? That's constant error variance. It's getting less consistent. Or do we have outliers? All right, so I want to look at a residual plot for our data. And then we'll decide how linear it is. Okay, so we know, right now, we could look at a scatter plot, right? But that is for our normal data, our XY data. For this to work, first thing, you have to have already ran the linear regression. which we did on our calculators. But that's the number one mistake people make. They enter their data in L1 and L2, and they try to graph residuals, and it throws up an error because you haven't told your calculator to find the line of best fit, and it has to have the equation of that line before it can calculate the error in it. So then,
Trap is dismissed at this time. Trap is dismissed at this time.
trap.
I heard track too.
Yeah, I was really confused for a second. Okay, so now everyone did run the regression line originally, right? Okay. So now you are going to go into your stat plot. Right, and we need to change it so that we are basing our y's off the residuals instead of the original list. Okay, so we are going to switch that into residual. So everybody's looking at this. Your X list is still L1. Why can't I remember? There was a shortcut for getting residuals. Why can't I do that? I don't want to go through the whole catalog. That takes forever. Why can't I think of my shortcut, guys?
How are we supposed to know this for the testing?
Well, I can get you to it, but there's forever if you have to go through the catalog.
That's like every settings change you can make in old calculators.
Mm-hmm. Still just scrolling through the catalog. Okay, I remember it. Okay, I've got it. Took me a second. We don't have to go through the catalog. Okay. So, when your X, make sure that stays as L1. For your Y's, you need to hit second, stat. And we want number 7. It says residuals. Second, stat. And it should say residuals. Okay? So now if we go to Zoom 9, here is my residual plot. Did everyone get that? So, is this a good model? What do you think? What's wrong with it?
It's bigger.
Yeah, it's getting more spread out as time goes on. So what that means is it was a good model at the beginning, but the deeper we're drilling, the less consistent it is. So, if we wanted to make a little comment here, I'd say this violates constant error variance. It is less consistent as time goes on. Now, does that mean a linear model is a terrible idea? Not necessarily. But it's saying there might be a better option. Or maybe we need a new linear model once we drill to a certain depth. What we are looking for on these is no pattern whatsoever. It should just look like a random assortment of dots. That's a perfect model. Patterns are bad. All right, any questions there? The last thing I want to talk about is influential. Influential is a point that would significantly change our regression line. All right, look at these 3 points. Here's my scatter plot. And then I've got case 1, 2, and 3. Is everybody looking at those 3 points there? Which of those do you think would not be influential? Okay, why is case 2 not influential?
Looks like it's on the right path.
Okay, it's pretty much on the right path. Even though its X is a lot bigger, if you're looking at your line, it pretty well follows it, so it's not influential. What about 1? Yeah, that one looks like it could be influential. What about this one? Yes, I would say that one's probably the worst because it's way lower than all the others. You know, this is definitely an outlier that would change my line some. So influential, what we could do is get our regression line with and without that point. You know, if I put in 0.1 and it just changes my line like that, was that a significant change? No, they're pretty well the same. But if I put in case 3 and it dropped my line down here, is that a significant change? Yes. Now, is there some gray area here? Sure, because how far apart do the lines have to be before it's influential? We're just giving it our best guess here. So I want to look at this. Suppose an additional data point is added to the drilling data. At a depth of 300 feet, it took 12.49 minutes to drill. Is this point influential? So I want all of you to go to your calculator. We have to go back to our L1 and L2. Okay. And what I need to do is down here at the end, I'm going to add in this new point, 300 and 12.49. And let's go ahead and run our regression line. So my new regression line with this point is 0.0212x plus 4.4433. The original line, okay, I have that over here. 0.01116. Okay, compare the old and the new one. Does it look like there was a change here? Yeah, our slope jumped up by 100th. Maybe that wouldn't be a big change if it went from like 3.24 to 3.23. But when our slope is so small to begin with, would that be a big jump? Yeah. You could also graph both of those, put them in your y1 and y2 and look at them on a scatter plot and compare them that way. But this does seem to be a significant jump. So would you call this an influential point? Yes. It was an outlier. It changed our line. Questions here?
Where did you get the original one from?
I pulled it from
Oh,
at the
you just
beginning when we, yeah, I pulled my screen off when we did the correlation coefficient earlier. Let's look at this one. A chemist has a 100-gram sample of a radioactive material. She records the amount of radioactive material remaining in the sample every day for a week and obtains this data. Determine if it's linear. So what would I do? Okay. Enter this in L1 and L2. So if I went to look at my scatter plot, one thing to mention, right now our scatter plot is turned on to residuals, right? If you ever want to look back at your original one, you have to make sure you change your Y to L2 again, which is just second number 2. So if you're wanting to look at that original data, you would have to go there. We could look at Zoom 9. This is what it looks like. Does that look linear? Fairly. It doesn't look terrible. Okay, let's check. Let's run our regression line. So if I calculate my linear regression, okay, look at our R value, our coefficient of determination. Does that appear linear? Negative 0.994, that seems pretty linear. So we looked at the scatter plot, it looked like a line. We look at our correlation coefficient, that appears linear. What's the final thing I can do if I really want to verify? We have to look at the residuals. So we ran our linear regression, so we're good there. So in our stat plot, if you did change it to look at the original scatter plot, you have to change your Y's back to residual. So just second stat would bring that up. So let's look at this residual plot. What do you think now? We had a lot of different data here. We had our original scatter plot, looked really linear. We had our correlation coefficient, which was pretty good, pretty close to -1. What about the scatter plot? What do you think? Or the residual plot? What's wrong with it? It kind of has a pattern to it, doesn't it? If it were truly a perfect linear model, there wouldn't be a pattern. We would have some points up here in the middle, some points down here on the ends, and so it looked more random. This one is kind of raising a red flag because we see a pattern. It means this is a really good model at the beginning and end. The middle is kind of an under approximation, which you could think about. If we drew our regression line, don't those middle points kind of sag down below our line of best fit? So that's showing up here. We can see that pattern in our residuals. All right, do you guys understand that? Kind of know what we're looking at when we see those residuals? So homework. This is going to be due at the end of class tomorrow. So tomorrow you are going to get class time to work and ask questions. As you finish this, I will go ahead and hand out our study guide for this unit, but you will have some class time. Okay, so you've got 10 minutes right now to start, but start in the next 10 minutes, but you don't have to